Well, welcome everybody to our oscilloscope coffee break. I hope you have your coffee or whatever your drink of pleasure is at the moment. My name is Steve Murphy. I'll be your presenter, moderator, for today's session. This is part 2 of a monthly webinar coffee break series, and it's going to run about 30 minutes, and feel free to ask questions. And also, I'll at the end of this, I will look at the panel setup. Actually, I'll kind of monitor it as we go along, and see if there's something I need to address as you folks bring it up. Your question panel is on the right side there. And just briefly, this is the coffee break series. Again, it's every Thursday at the last Thursday of the month. And hey, we're just taking a break, and we're going to talk about a particular subject around electronic test equipment, and specifically oscilloscopes. And today we can see here number 2 here for February is optimizing your display and using your cursors in measurements. This is me, Steve Murphy, and enough said. This is the optimizing your display. So we'll focus really again on that display, and getting your oscilloscope waveforms displayed in a way that give you the best measurements. And it's really all about being efficient and at debugging and validating a circuit's electrical properties. So here where I'm setting the stage, this is the agenda that we will follow, and we'll focus first on the displays, and then we'll move on to making measurements, different ways to do that, and we really, again, we want to try to pick some things out that make, that are good to remind ourselves to get the most out of using our oscilloscopes. And so that's really what we'll be covering here. So I am setting the stage right now for your break. Again, thanks for joining us. What do I have set up? What am I using today? And so this is a WaveRunner 8000 HD. In fact, well, it's a 2 gig scope that I'm using today, and that's the sample rate. And the memory length varies from 50 million to up to 5 gig. And you have 8 or put 2 of them together, and then there's 16 digital channels. Okay, so, but anyway, what I'd like to just show you is, let's go to my desk. And this is my workbench. Hello, this is me, my hands at least. And what we have over here is, this is the oscilloscope that we're using for these coffee breaks. This is the WaveRunner 8000 HD, and this one happens to be an 8-channel, and this is Windows-based. It's running Microsoft Office, so you'll see me use PowerPoint. I'm tied into my home network here, so I'm running my browser for this webinar session, this GoToWebinar session, and the camcorder software is running, and the oscilloscope, most importantly, software will be running. So I'm going to be bouncing around those different applications here, running on this oscilloscope's PC. And probing. For today, what I'm doing is, I got channel 1 and 2. I have just regular × 10 passive probes, but I also have on channel 3 and 4, I've got a differential probe here. This is a high common mode new probe from Teledyne LaCroix. But anyway, that is being probed this D-skew calibration source, and I'm also using a current probe as well as a signal. So I just wanted to start off with 4 signals, and then over here on the side here, I've got this other little generator that generates a number of different signals that we'll use as well and probe that. So that's my setup for this coffee break, and I think we're good. Actually, you know what I can do is just, I will and just zoom in on that. And so this is a much better view, I think, of 2 probes, channel 1 and 2, and then differential voltage, and then a current probe. Okay, all right, very good. Let's go to the, back to PowerPoint. All right, so onto the display. There's the agenda. Now, when we're viewing waveforms, of course, here we go. We've got one channel display, and you see that there is one grid. And so this is fairly short, and we can see the details pretty well on that waveform. But what happens when we want to look at 4 channels and 4 waveforms? And as we get more blocks of data and look at wider time windows, right, you're going to run into, I can't see all those details and I want to see them. And so these 4 channels now need to be reduced, right? And so we're going to still use this one grid, and we are going to see that we're, using much lower amplitudes on these signals within the one grid, so we don't have any overlap, so we can do the details. So is this good or not? And so that's what we're going to dive into here. And so to do that, let's go back to, well, I haven't really not introduced you to, this is the oscilloscope. And this is, well, I can do this. Let's go to windowed. And so you can see I have the scope application running. I'm going to go back and maximize it. I'm looking here at 4 channels, as I mentioned, and I showed you on the setup. Let's go to normal trigger. And so we're running live. And channel 3 is disconnected, I believe. And hang on one sec. Murphy's Law always follows me around. There we go. So these, the channel 3 and 4 are asynchronous to channel 1 and 2. Channel 1 and 2 are hooked up to the calibrator. 3 and 4 are asynchronous. So I'm just going to go ahead and do a single shot so we can see these are our 4 waveforms, and we've reduced them just like the slide set showed. We reduced the amplitude to say 1/4 of the size. So we can't have the waveforms overlapped. So therefore, we reduce the amplitude. Well, what does that really mean? Where this is in this case, from the bottom of the display to the top, there are 4,000 quantization levels in this 12-bit scope. 8-bit scopes, 2 to the 8th would be 256 quantization levels. So as we take a sample, we digitize it, and we create a digital value for it, put it into memory, and do that at the sample rate of the scope. Then we're all we would build up these waveforms. So this is good, right? But what if we wanted to make amplitude measurements here? And amplitude and even timing measurements are good. Did us reducing the amplitude of these signals affect our measurement? So let's dive into that. So what I'm going to do is I'm going to flick off channel 4 here and 3. So we're now at these 2 waveforms. Now channel 1 and 2 again are tied together to the calibrator. And now let's go back live, and I'm going to disconnect this DSQ source. It's adding a little noise to my channel 2. There we go. And so we are live. But what I'm going to do is take channel 2. I've highlighted the descriptor on the bottom. I'm with my, well, I could use it with my mouse, since you can see me do that. And then what I'll do now is change the volts per division setting on the scope to 1 volt per div. So same signal, and now we're at 1 volt per division. Well, what does this do for us? Let's stop the scope, and I want to compare our smaller acquisition on channel 1 at 1 volt per div versus the 200 millivolts per div on channel 2. So let's do this. Let's touch channel 1, bring it down here, and let's increase using the vertical zoom. Let's get to the same time scale. And when we look at that, and let's just, well, actually, let me bring this back down. Okay, so there's the 1 volt per div. And just to make it really obvious, I'm just shrinking it down a little bit more. I've got some noise in my, looks like from something here. There we go. And let's just stop the scope. And let's now expand this. Look at the noise on this signal compared to channel 2. And when we zoom in on this, let's take a look at those in a little bit closer detail. By the way, if you look down in the bottom right, I am at 500 nanoseconds per div now at 1.25 gigasamples per second. And each of these waveforms have 6 kilosamples, 6.25 kilosamples of memory to define that. But so that is that signal. I am, oh, we have the same. Let's do this. I want to go back at this again. Let's go normal. Single, and let's back to channel. So we captured it at 10 times smaller, if you will, a tenth. There we go. That's a much better view of making my point here. So our setting here on channel 1 is 200 millivolts per div. Because we're using a zoom, but we acquired it at 2 volts per div. Look at the amplitude noise we're now seeing on this. We've just taken our 12-bit scope and made it a 10-bit scope. And because if we have 4,000 quantization levels from the bottom to the top, each division's 500 quantization levels. But if we're only using a fourth of it, that 4,000 becomes 1,000 that we're defining the acquisition of channel 1 on. So now 2 to the 10th makes it a 10-bit scope. And it's even worse if you folks are using a 8-bit scope. So instead of 256, a quarter of that, 64, you've made your 8-bit scope a 6-bit scope. So the amplitude measurements from your display, by shrinking it with the purpose of today's webinar, coffee break, is to really, if you're not really trying to make accurate amplitude measurements, then shrinking the waveform is just absolutely fine, right? There's no problem, and you'll be able to capture that. And just do this one more time, yeah, and let's go get some more data as my point. So we could slide the waveforms as we want and move them up and put more waveforms on and all that. So no problem. But just be aware, it's good to know. We stop the scope and we expand this. We see really the increased noise. And I also want to point out, I'm zooming in for a reason, right? I also wanted to show you, look at the timing measurements, right? We are also hearing that channel 2, when I reacquired, it's got a little noise on it from my environment here. But at any rate, look at the rise time measurements of the yellow waveform. And we can see, geez, rise time measurements will be affected by that, or fall time. So not only, my point is, does the amplitude, accuracy, affected by the acquisition of low amplitude waveforms, timing makes a big difference as well. I think that's describes that. And let's go back to our slide set to show you that. So there we go. And now the slide set will be available to you, and we will send that to you as a link afterwards. And but anyway, this is my main points here that you'll see from 256 levels versus for an 8-bit scope. And when we reduce that, we really turn into a 6-bit scope. And then on the left is where we do the 12-bit scope comparison as well for that. What are we going to do to improve that and still see the 4 waveforms without overlapping them? Well, take advantage of an oscilloscope's multi-grid display. Here we're showing you a quad grid, 4 grids, and each grid, even though the waveform is about the same as we had before, the sensitivity was higher. Sensitivity and our peak to peak within the grid is mostly filled from the bottom to the top. Therefore, we're using the full dynamic range of our oscilloscope. And we're doing that for each channel, so we're not overlapping, which was our goal, but now our measurements were acquired at higher sensitivity using the full dynamic range of our 12 or 8 or 10-bit scopes, but we are now just showing you the amplitude here. The much better way to acquire it. And so if we go back to the scope and we go back live, our sensitivities are, let me do this. I'm going to maintain that. Let's go to display and let's go to dual grid. Let us go to quad grid, and you'll see that all of these are full 12 bits. Here is octal displayed this way. All grids are there. And so we can acquire more waveforms, 4 or 8 channels in this case, or do zooms or do math and all of that and utilize these grids. So don't forget, multi-grid is as an option. If you're trying to make, if amplitude measurements are very important and horizontal timing is important when you have more than one channel displayed and you don't want to overlap. So that's just a quick little reminder on that. There is on the scope the ability to go to, let's just do it, come back to the oscilloscope, even go to display too. There is many choices for you to display, and including, let's just jump right ahead here, 16 of them. So every one of these, again, full dynamic range, more waveform displayed without overlapping. Okay, so bottom line again, if you don't want to overlap your waveforms, and reducing the amplitude is fine, which is okay, right? And because you're not making accurate measurements, you just want to see the waveform, then no problem to do that. But if you do want to get and improve the accuracy, then utilize the full dynamic range of the amplifiers or scope by maximizing the bottom to the top of the waveform within a grid. Okay. Back to the presentation. Okay. All right, and there is a persistence display mode as well. So as you can turn that on, you can shut that on and off and be color or analog type of display and vary the persistence and see the last acquired waveform or not. Just be aware too that in your display, part of this topic is that persistence is an option to see the varying amount of signal excursions here. Jitter, noise, all of those things are displayed here. Okay, so that is that. On to the next thing. So now what we do is we've got the signal. Now what? Let's make some measurements. Well, you can just use I say like there's 3 different ways to do this. One is, hey, just use the waveform grid. You can just go back. Let's go back to our scope over here. And let's go back to, I'm going to hit display auto grid so that the scope will automatically, the scope application will automatically assign a waveform to a grid. And we're good there. But so what I might do, I'm going to just take like channel, we might just use one of the 3 ways to make measurements is just use the waveform grid, position this, the waveform, let's put it over here, we're running live again. And then we can say, okay, we know that each grid is that. And so we're at 500 microseconds per day. And we can make some really ballpark measurements of that. So we can see that that's like 3/4 of a division. So 3/4 of that puts it at what, 350. That's really, not very accurate measurements, but then same thing with the amplitude, we can move it and change the offset so that we are on a grid, and therefore we're going to make measurements. So this is pretty much what you're pretty used to doing. So that's one of the 3 ways. Another is go ahead, let's go do cursors, and we could do it horizontal or absolute cursors. And so I think you're all pretty familiar with the use of cursors. They're really easy to use. They give you a good ballpark, right? Timing. Here's one full cycle right here. And so we look at the dash dot dash and dashes and also the arrows to indicate on each waveform, at least on this Teledyne LaCroix, their scopes might display the data a little different depending on which scope you have. But we have the down arrow, the up arrow right there. These are the voltage values at each of these points. Let's just move this just down a touch just to get it down. There we go. There we go. I'm just using the cursor, and I could use the knobs. I'll use the mouse to do this. And therefore, now we can see the delta difference can be displayed here in the waveform descriptor and off to the right. Of course, you'd make timing measurements. There's the difference in time between the two cursors. By the way, the cursors show you the time from the trigger. For right now, the way I have this set up, the 0 delay, the trigger point is almost 50% pre-trigger, 50% post-trigger. This cursor tells me the time to there. This cursor tells me the time to there. They're both minus, right? You can see them minus the way that I have the cursors positioned. If I change their locations and switch them, it would turn into positive. But this is the timing to the 0 delay position. So that could be totally off screen if you want, and it'll as far as the delay, and you can still make measurements. It will tell you the timing from the trigger point. We are triggered on an edge trigger, by the way, on channel 1. In this case, it's 700 millivolts positive. Okay, so this is this timing, and I'll move this along a little bit more. There is, you can see that our calibrator signal, I set it to 2.5 kilohertz as its output. Okay, so there's that, and then you can obviously go to amplitude cursors. If I come back just quickly to the PowerPoint to keep this moving, we can see this is doing the peak-to-peak amplitude cursors. This is showing you ripple as an application on a 1.5 volt power rail. So that's an example of using cursors. This is using the time cursors, and we have two different signals, and we're going to measure the time between the two, which is read out as 33 nanoseconds. Okay, and then here's another application for cursors before I move on. This is the setup time from the clock to the data, and that is also measured by hand, visually, on-screen readout, on-screen positioning, but we're measuring 900 picoseconds for that clock to data time. So those are examples of using parameters. Cursors, I'm thinking ahead. But parameters will give you much more accurate, higher resolution measurements. So we're going to move on now to parameter measurement. So pretty much the same as parameters, but definitely more automated and more accurate. What parameters do is they can look at the entire waveform itself and then make measurements on every feature. You can say that every scope operates a little bit different, but we have whether they show statistics or not and how they measure that is my point. So what we have turned on here is amplitude, frequency, duty cycle, rise time, and fall time. And we do have that's the last measured value. This is the mean of within a waveform. Let's go do it live, actually. So let's go back to the scope. Let's go to just add a measurement here. Well, you know what? I'm gonna recall a lab notebook. I want to work with this unit right here. I'm flashing this back, and while it is coming back into the scope, it changes the panel setup. I am reprobing. I'm grabbing that little circuit board that I was telling you about and showed you. I'm now made connection to it, and if I hit normal, I should be running live. Yes, this is a pulse width modulated signal that we're looking at to go through the next topic, which is measurements. So this is, let's just stop that for a sec. This is the statistic table, but I have peak to peak frequency turned on, and then width, duty cycle, and rise time. We could go ahead and just add whatever you would wish here, right? So, you know, we could do whatever RMS or do the slew rate, whichever, skew, time level. I'm just thinking here of, so actually let's just do width. I'm gonna do width and I wanna do it of another channel. So I could just bring over, if I had, well, let's turn on a channel. We could take channel 3 and just move it right here and do width measurements. Of course, there's nothing there right now. So anyway, we could, let's take 3, turn on 1, and we do need to grab this and let's go get some data. There we go. So we have channel 1 that's live, so we just grab channel 1, put it over here, and now we have measurements on width. So of thinking what would be the best thing to tell you that would be of use from what you might already be aware of. I don't know everyone's skill level, but on this webinar, but again, my point here is you have a wide assortment of measurements that you can add to a table. You can make multiple measurements of the same waveform. Don't forget under width, I just picked on P6. Don't forget to the right. Here off to the left on this particular oscilloscope shows you the source and the measurement selected, but on the right is gates. And don't forget in this, when you look at your gate, look off to the left here. And let's simply just shut off 2 at the moment. Okay, since I picked on this, this is one gating cursor. Gating measurement, I can move this over, yeah, and then here off to the right is the other. So now the table has been duplicated and the measurement is duplicated, the source is now channel 1, and I also have the gates turned on. So within this gated window, you'll notice that now instead of being like 14 widths that occurred, so every occurrence, every width is being measured, calculated, the last one's displayed, the value of all, in this case 14, or there's peak to peak. Let's go to this width over here. 359 were acquired. The last measure's that. The total mean of this many acquisitions is this. We have the min and the max displayed. So there's 359 measurements. But now what we're doing is we're showing you gating measurements. So again, just to try to point out some things during this coffee break that could be useful, that are a little non-standard, that some of our customers and users and forget about, is that go ahead and put down use the gates to define the measurement window. And they can be different for every scope, for every parameter, or you can have them all the parameters be defined. You can define all the same location as well within the waveform acquisition if you vary the gates. I'm going to just go to gates here and say, there we go. Let me reset this, and I'm going to turn on channel 2 again, shut off channel 1, and make for my next point. Okay. Clear sweep, single shot. Within this waveform, you may be acquiring it as a single shot. And so that's what we did here. But let me pick on width, duty, and rise time. There are 27 of each of those, 28 rise times in this single shot acquisition. Amplitude, or excuse me, peak to peak is a complete waveform measurement. So we have peak there. So don't forget to use in your oscilloscopes the statistics. They're very helpful to find any outliers that are there. So a statistics table gives you the range, the min to the max and the mean, and we can see the values there. Yeah, so and so we can see 168 nanoseconds versus 225 microseconds. So there is a real discrepancy here that's going on. And if I let this run, we can see that, well, we build up a little histogram, which gives us more insight, not to the range as this statistics table does, but the distribution. How are these measurements changing? And so you'd use this histocon and histogram on oscilloscopes to give you insight. And then now that you've found an outlier without formally having to trigger and look for things, statistics like the table and the histogram really help you identify any outliers. So this width defines zero width, the widest width. Most of the measurements around here, which we could say that it's this 190 microseconds. But look, there is a little bin here to the left that shows we're 167 nanoseconds. So there's that right there. And I'm going to pick on this because I know I'm running short on this coffee break. So just if you would allow me, I'm going to turn on a track. I'm going to use F1, and there it is. And so this track takes the width measurement in P3, and on this single acquisition, it measures every value, plots it as a new waveform, which is now this math function F1. And so don't forget to use those. They show you how the value in this case of width is changing, but you can see that we do have something going on here. And if we look at that in a little bit more detail, let's go ahead and zoom in on both. And we can see indeed there is right here a glitch, and you can see that's where it dropped down in the math function. So it isolated and located where exactly the glitch was in the acquisition. So important to know, important to locate. And if I had other channels on 3 and 4, don't forget you can correlate this problem with other channels, whether it be a mixed signal input or other channels. So that is using a track in the parameter, and we can trend multiple acquisitions, same thing, except it's going to save data from previous acquisitions and build up a new math function called trend. And of course, the histogram is a live version of these histocons. So I am just using this coffee break to just say, hey, don't forget there are other features in oscilloscopes that you can use to help you validate. If I come back over here, this is really the backup to, I won't show that now, but you can see we've got the parameter values with the track displayed. Here I went to a quattro grid, and I'm thinking too, what would be really good too is to use these rise time measurements and back to the front of the presentation, the coffee break. It would be interesting to look at the statistics table of the zoom of the edges from a waveform acquired at very low levels, very low amplitudes, when it should have been using the full dynamic range of the scope. And you compare those rise time or fall time measurements, that would be a good thing to show you too, but I know I have to, I might just still show you at the end here. But at any rate, this is quattro display. Here's the waveform. Here's that glitch we found through the use of a track. And then there is a histogram, a live version of this histocon. So don't forget these tools are available to help you locate, isolate the errors, the problems. Let me just take a second here. Yes, so let me look at the thing on that. So let me just do this too. Let me come back to the scope. I just would like to do this. Let's move this here. I'm going to go File, and I'm going to just take an extra 2 minutes to show you this because I believe it's really pretty important. I'm going to recall a lab notebook, which is that back to that second one. Flash this back. Come back to my probe setup, which is the calibrator. While it's doing that, and we're good. We're going live now. Yep, and we're going to shut off 4 and 3. And channel 1 and 2 are required at the same. Let's take and require this C1. Now that we've covered parameters, let's use them back on this waveform. So channel 2, let's move this down. Increase the sensitivity back up to 200 millivolts. We're using the full dynamic range of channel 2 where we're not in channel 1. And then now let's do a single shot stop. And then when we compare, look at this, P1, I said, what's your max on P1? And let me just go, there's the max of C2, frequency of C1. Yep, so we have, so I wanted to look at, I mentioned rise time. Look at the rise time of P6. Let's turn on statistics as well. This. What is our statistics telling us? That on P6, which is the rise time of C1, we can see that our last measured is 68 nano. Our mean is this, and our max and min are here. And so we can see that there is, and compare this to channel 2. Look at the deviation around this mean, which is what SDEV is. So our mean rise time measurement is 65.4 nano. We're deviating around that at 2.96 nano, but because our what? C1 is very small in amplitude. C2 is 67.8 nanoseconds, and look at the deviation of these 104 measurements. Only it's 710 picoseconds. So if you want accurate measurements, then just be aware, you can be set that amplitude using the full dynamic range makes a difference for both amplitude measurements as well as timing measurements. Okay, I just needed to show that to you. I know we're close on time here and have hit our time. And so these are a summary. I think I've already nailed that pretty well with don't forget about histograms, tracks, and even trends in your parameters. So there is, as I just do a quick wrap up here, go online, and this will be recorded as well as other webinars will be recorded, and there's quite a resource available to you here. The other coffee breaks, but all kinds of other topics and applications are listed there. Go ahead, the application that you saw me use, the scope application, is called Maui, and you can download a Maui Studio, which is just like running the software that I'm running right now, that you could do it on your PC remotely, and we can turn on just by letting us know what your serial number and ID is, and we'll send you back a license to turn all these other features on. Okay, really appreciate your time. I moved a little fast and bumped around a little bit, but I hope you found this was helpful. Let me now look at the questions here. And would it be possible to use the cursors to define the gate for the measurements is the question. Yes, for sure. Well, actually what you'll be doing, we call them parameter gating cursors, right? So when you go in here and you select any one of these, like this, I just have to move this panel away here, okay? So like a rise time measurement, you can define which rise time. Don't forget in the gates right here, this is where you go to define the gates. You'll see, at least on the Teledyne LaCroix, you grab your gates, your gating parameters right here, and then you set the gates as you wish. You can see now that we're down to 2 rise time measurements again. So that is, if you have any other questions, I'll just give you a moment, but it looks like that was the one question that I had. Again, if you, after the fact, you have some questions you'd like to ask me, there is my email address. And again, really would like to thank you for attending this coffee break. I guess we get to all go back to work now and continue on with our day. We look forward to talking with you and at our next webinar. Again, thanks for your attendance and interest.